Alright, so in the second part of this week's online videos, we are going to talk about a few relationship types between the compound factors that we have learned so far. The first relationship is the reciprocal relationships, and actually most of these we already know, but for the sake of repetition here, we will say that most of the compound factors that we have learned are computed over a reciprocal relationship. For example, because we have the single payment compound amount factor column in the compound interest tables, we can use its multiplicative inverse or the reciprocal to calculate the single payment present worth factor. Similarly, what we is the uniform or uniform series compound amount in the table, but we can also use that value and take its reciprocal to calculate the uniform series sinking fund factor. We have A over P, which is the uniform series capital recovery factor, and it can be used to calculate the uniform series present worth factor, again with a reciprocal relationship. And we have the gradient series factor, where we use the gradient and compute equivalent constant amount of payments or the uniform series payments. We can use its reciprocal to do the inverse operation. For example, if you are given a uniform series, and if the question asks you to determine the gradient amount with respect to that uniform series, the equivalent gradient amount. So you actually, the question is asking you to form a gradient series, and you can use the reciprocal of the A over G, and you can calculate G over A to convert the uniform series to a gradient series factor, a gradient series amount. All right, so this is the first type of relationship. Now we can move to the second type of relationship, and these relationships are called multiplicative relationships. Now, we know that there are various multiplicative relationships. For example, if you multiply the uniform series sinking fund factor with a single payment compound amount factor, then you will realize that in the ratio of A over F and F over P, the F's here will cancel out, and what you are going to get is A over P. So uniform series, single payment compound amount factor multiplied with the uniform series sinking fund factor, what you are going to get is the uniform series capital recovery factor. Now, before moving on the others, I would like to show something about this relationship in the compound table, compound interest table. So I'm just going to share table with you. So right now you're seeing the table. In this table, we have a single payment compound amount factor here and the uniform series compound amount factor here. Now, if you are careful, you will realize that when you divide the value in the first column, the value in the second column, then you are going to get the value in the third column. So here, for example, 1.01 divided by 4.015, you get approximately 0.25156. So how do we get it? Actually, reciprocal of F over A is A over F. And when you divide the value in the first column to the second column, you are actually multiplying F over P with A over F, and then it becomes A over P. So we are basically practicing the relationship that we have explained in the presentation file here. So if you divide the value in the first column to the value in the second column, you are going to value in the third column always. Okay. So let's go back to our presentation file now. Okay. So similarly, we can build other type of multiplicative relationships. For example, if you multiply the uniform series compound amount factor with the gradient series factor, what you are going to get a new factor which is called f over g, and that factor can directly convert your gradient series to the future value. And similarly, if you multiply the uniform series present word factor with a gradient series factor, again, you are going to get a ratio, new ratio, which is called P over G, which is directly convert your gradient series to the present word factor. So you can build these relationships, and by relationships, you can make direct conversions from a series type to a future value or a present value, or from a series type to another series type. You can make these fast conversions, and most of the values that are necessary to these calculations are available in the compound interest. Okay, so we are going to move on with another relationship. Again, this is classified as a multiplicative relationship, and it says, suppose that we have the number of investment years and decomposed into two phases. First, we have N1 years, first N1 years, then second N2 years. So, for example, if we have a 10 investment years, we can decompose it into 7 plus 3 investment years. So, just like that, we have a decomposition of the time horizon into two integer values. Now, it says the single payment compound amount factor for N years can be computed by the single payment compound amount factor for the first N1 years, and then multiplying it with the single payment compound amount factor for the next 2 years. Basically, this figure explains the formulation there. Now, our objective is to convert this principal value to the equivalent future value in the end of N years. So what you can do is, you can first convert your principal to a future value in the end of the first N1 years, then assuming that that value is withdrawn and deposited again immediately, and you can multiply that value with another future value factor or compound amount factor for single payment for N2 years to convert it directly to the final value. Okay. So instead of this direct calculation, you can perform an indirect calculation to calculate the single payment compound amount factor for N years. And the reciprocal of the above equation will also be true, which means you can also convert the future value to the present value for N years. So instead of calculating the single payment present word factor for N years, you can calculate single payment present word factor for the first N1 years and multiply it with the second N2 years single payment present word factor, and that value would be equal to the present word factor for N years. Okay, so as long as the interest rates are constant, the interest rates are the same throughout these years. Okay. Now, why do we use it? I mean, you may ask this question. I mean, don't we have these values in the table, or can't we calculate these values through formula? Yes, you can use the formula at all times, but unfortunately in the tables, we do not have all the values. I mean, if you check the tables carefully, there are some missing rows. For example, in this question, we are asked to determine the value of single payment compound amount factor 8% interest rate for 37 years. And it asks us to calculate this value for using a compound interest table. Okay. Now, what we are going to do is, we are going to check the table for that, but when you check the table, you will realize that in the page that belongs to 8% interest rate, there is not a row that corresponds to 37 years of investment. So we are going to look at in short. Now, what you can do is, you can use the third type of relationship, multiplicative relationship, and you can say that the single payment compound amount factor for 37 years under 8% interest rate can be computed as the multiplication of the single payment compound amount factor for the corresponding interest rate for 7 years times the same compound amount factor for 30 years. So here you can take these two values from the table because we know that there is a row corresponding to 7 years and 30 years, and we can take these two values and multiply them to calculate the single payment compound amount factor for 37 years. Now let's go to our compound factor table. All right, so we have what's f over p, and for which interest rate we are looking for? 8%, right? So this is the page that we would like to see. And as you can see, if you go down, you will realize that there is not a row corresponding to 37 investment years. And for 37 investment years, we expect the compound amount factor to be somewhere between this value and this value. So it should be somewhere between 14.78 and 21.72. Now, what we can do to calculate that value or to approximate that value is we can check the 30 years single payment compound amount factor, which is 10.0627, and also check the 7-year single payment compound amount factor, which is 1.738. Now, taking these two values to our solution, I'm going to multiply these two values, as you can see here in this presentation file, and the single payment compound amount factor under 8% interest rate for 37 years would be 17.2455. Okay, so the previous relationship was shown in this question. Now let's do the same for another question. It says, how much money should a person deposit into a savings account that pays 1.5% interest per year that compounds annually, so she can have $100,000 in 38 years? So this time we are going to do the opposite operation, right? So in the end of 38 years, we would like to have a $100,000 in our account in the end of 38 years. Now, how much should we deposit in that savings account right now? The question is asking, and the corresponding interest rate in that savings account is 1.5%. Now, the numerical value for the single payment present worth factor for 38 years is not available in the compound interest table because we do not correspond to that many number of investment years. But what we can do is we can decompose 38 into two phases, the first 19 years and the second 19 years. And basically, the single payment present worth factor under 1.5% interest rate for 38 years would be the product of the same present worth factor for the same interest rate under 19 years. Okay. And since both of these values are the same, we can simply write it as the single payment compound amount factor under 1.5% interest rate for 19 years to the power minus 2. So we are not using to the power 2, but minus 2. So we are calculating the reciprocal of it. And you know, in the table, we have this f over p for 1.5% interest rate for 19 years, which 1.3270 if you check the table. I'm not going to show that right now, but you check that table right now if it is printed out. Now, if you take the minus 2, to take the power at minus 2, you are going to calculate our value of interest as 0.56788. Okay. Now the question asks us this: if the future value is going to be $100,000, what should be the present value? And we need to multiply that future value with a single payment present worth factor for 1.5% interest rate for 38 years. And that value is approximated by the multiplicative relationship. That makes 56,788. Now, the trick in this question is this. In the previous the value, the number of investment years was 37, and we have decomposed it into two parts as 30 and 7. You could have also chosen another decomposition. You could have decomposed it into two parts such as 20 and 17. Okay, it does not matter. However, we have 38 here. 38. Now, in different ways, you can decompose 38 into two parts. You can choose 10 and 28. You can choose 20 and 18. You can choose 30 and 8. Okay, so there are many ways, but I intentionally have chosen 19 and 19. Why? Because if I choose this decomposition, I'm just going to check only one value from table, not separate two values. So I'm just going to check only one value, and that is just going to shorten my solution time. But this does not compose this into 19, and this does not mean the approximation error is also minimized. Unfortunately, we can be sure in which type of approximation or in which type of decomposition the approximation error is minimized. Therefore, this is just by chance. I mean, you can choose any decomposition. You can decompose this 38 years in any way you like. However, if you really want to get the exact value for this compound amount factor, please use the formula, okay, not the tables. Okay, so we are just going to continue with another relationship. This is just going to be relationship 4. And in this relationship 4, we are going to say that the uniform series compound amount factor f over a under I% interest rate for n years can be calculated as the sum of f over a under I% interest rate for n1 year plus f over p, which is single payment compound amount factor for I% interest rate for n1 years, and plus the same compound amount factor for n1 plus first years, 1 years, and so on and so forth until n minus 1 years. So basically, this relationship explained here is described in this picture. Now it says we have a uniform series of payments for n years total, and we would like to calculate the future value of these n years of uniform series. Now we decompose these uniform series into two parts. The first part is the last n1 years of payments, and the first part is the first n minus n1 years. Now the last n1 years is discounted to the future by multiplying a single of this, a single installment here with a uniform series compound amount factor for n1 years. Okay, so altogether these uniform series can be discounted to the future, and the remaining payments can be discounted to the future individually by one by one by multiplying each installment with single payment future value or the compound amount factor, which is f over p under I% interest rate. Now, from this payment to the future, there are n1 years. From the previous payment, there are n1 plus 1 years. From the previous payment, there are n1 plus 2 years. From the first payment, there are n minus 1 years. So these values of n1, n1 plus 1, and n minus 1 are coming from here. Basically, in a short formulation, we can say that the uniform series compound amount factor for n years is equal to uniform series compound amount factor for n1 years plus the summation of single payment compound amount factors from n1 years to n minus 1 years. Now I am just going to explain this from the compound interest tables again. And I'm going to share that table with you. Now, we can choose any page to explain that. So let's just say we are interested in calculating the uniform series compound amount factor for 10 years under 8% interest rate. So this is our objective. We would like to calculate 14.4866. So you can do it like this. You can decompose these 10 years into two parts. So for example, 6 plus 4. For the last 6 years, you can choose f over a 7.3358, and you can sum that value with single payment compound amount factor for the 6, 7, 8, and 9 years. So basically, what I'm trying to say is I sum 7.33 here, and 1.58, 1.71, 1.85, and 1.99 here to get 14.48. Okay, so any f over a value starting with that value, if you go to the first column and sum the values up cumulatively and stop at some point, let's just say you have stopped at 9, in that case you are going to get uniform series compound amount factor 14.4866. Okay, now you can use this trick to calculate any f over a value which is not available in the table, right? But for that you also need the values for f over p in that. So let's just go back to our presentation file and see if there is an example about it. Now it says determine the value of f over a under 8% interest rate for 37 years using the compound interest table. Okay. Now, the numerical value for f over a under 8% interest for 37 years is not available in our table because there is not a row that corresponds to 37 years, but we can use the additive relationship that we have explained a while ago, which would be the uniform series compound amount factor for 7 years is equal to the uniform series compound amount factor for 35 years plus single payment compound amount factor for 35 and 36 years. Now, if you sum these three values up, you are going to get the uniform series compound amount factor for 37 years. And the first value is available in the table. The second value is also available in the table. But the third value is not available in the table. But in order to calculate that, what I can use it, I can decompose this single payment compound amount factor using a multiplicative relationship as the product of single payment compound amount factors at 35 and 1 years. And as you can see, we have this value and this value is same. One of them is multiplied with the single payment compound amount factor for 1 year, which is 1.08 automatically, because you know the interest rate, and actually no need to use formula, no need to check the table for that compound amount factor. And there is 203.0702. Okay, so you see we have in this question, we have not just used an additive relationship to quote the single payment compound amount factor. We have also used the multiplicative relationship that we have explained a few pages ago. Another additive relationship can be explained through this formulation. Again, if we suppose that we have a uniform series and we are interested in calculating the equivalent present value of that uniform series under I% interest rate for n years. Now, what we can do is we put that uniform series again into two parts, and the last n minus n payments. Now, the first n1 years can be directly discounted present value by multiplying a single installment size uniform series present worth factor under I% interest rate for n1 years, and each of the remaining installments can be handled individually. We can discount each of them one by one by multiplying with a single payment present worth factor P over F. The first installment will be multiplied with n1 plus 1 because there are n1 plus 1 years here. And the second one will be multiplied with n1 plus 2. And it goes on like that until the last one will be multiplied with a P over F for n years. Okay, so actually the above formula is explaining this. A uniform series present worth factor for n years is equal to a uniform series factor for n1 years, where n1 is less than n, of course. And the remaining installments can be handled by a single payment present worth factor for N1 plus 1 years, N1 plus 2 years until N years. So we are basically summing all these values up. Okay. Now, of course, these values are not directly available in your table. So I cannot show how this works through the table. Basically, we have this short closed form of formula, which gives us a present uniform present worth factor for n years can be decomposed into two parts. A uniform series present worth factor for n1 years plus the summation of single payment present worth factors under the same interest rate for n1 plus 1 years to n years. Now again, we can practice this in this question, and we can calculate the present worth of $10 annuity for 52 years under 2% yearly interest, compounded annually. So this time we have, so if you go back to this cash flow diagram, we have 52 years, and the installment size at each year is $10. Okay, for 52 years, we would like to withdraw $10 in the end of each year, and the interest rate corresponding that savings account is 2%. Now, our objective is to calculate the present value of a uniform series $10 in the end of each year. We can multiply that 10 with a uniform series present worth factor for 2% interest rate and for 52 years. Now, that P over A can be decomposed into two parts. A uniform series present worth factor for 50 years, which can be searched through the table, plus P over F under 2% interest rate for 51, and then plus for 52 years. Now, then what we can do is, in order to calculate the single payment present worth factors for 51 and 52 years, we can again decompose each of them into two parts. 51 can be decomposed as 50 times 1, and 52 can be decomposed as 50 times 2. So this is the multiplicative relationship that we have learned earlier. And then the rest of the calculation can be done by looking through the reciprocal of each value, because none of these values are directly available in the compound interest table. So P over A is going to be calculated through the multiplicative inverse of A over P value, and all P over F values are going to be calculated through the multiplicative inverse of F over P values. Now, each of these values can be searched through the compound interest tables. A over P for 2% interest rate for 50 years is 0.03182. F over P for 2% interest rate for 50 years is 2.6916. And F over P for 2% interest rate for 1 year is simply 1 over 0.2. And the other one is 1 over 0.404. And taking the reciprocal of each of these values, you get a 32.14815 as the uniform series present worth factor, and the final value is 321.48. Basically, if you invest $321.48 into a savings account that pays annual compounding interest rate under 2%, then in the following 52 years, you can withdraw $10 of annuity in the end of each year. Now, we are coming to the final relationships, which is relationship 6. Here it says the uniform series capital recovery factor, A over P, is equal to uniform series sinking fund factor plus I. Okay, so capital recovery factor is equal to the sinking fund factor plus I. Actually, the proof is very simple. Now, check that out. This is our capital recovery factor formula. And in that capital recovery factor formula, I am just going to do this simple trick. I am just going to add and subtract I to the numerator. And if I do that, and if I take I multiplier into a common parenthesis, Okay, so I is the common multiplier here in the first two terms. You are going to see that we are going to have I over 1 plus I to the power n minus 1, and then plus I. Okay, and I over 1 plus I to the power n minus 1 is the uniform series sinking fund factor. So this is actually not very hard to see through. And let me explain that situation through the compound interest tables. Now, in any page of the compound interest factors here, okay? So if you have a f over a value here, f over a value here, you just need to calculate the reciprocal of it, which is, for example, 1 over 5.8666, and then if you add 0.08, if you add 0.8 to that value, you will get a value. Okay, so the negative inverse of the second column plus the interest rate as decimal will give you the third column. I mean, you can check that easily. For this value, the multiplicative inverse of 1 is 1. And if you add 0.08, you get 1.08. Okay? And you can try it for any value in that row. For example, 1 over 27,484 point something. It is going to be equal to a very, very, very small value. A very small value, right? 1 over this value is going to be a very, very small value. And if you add 0.08 to that small value, you are going to get something like this, 0.08004. So as increase in the second column, f over a values are increasing in the second column, the values in the third column are converging to 0.08, which is exactly the decimal interest. Now we are going to come to that relation in the next page, in the next pages. So let's go back to our presentation file. Now it says calculate, the question says calculate the uniform series capital recovery factor A over P under 8% interest rate for 5 years using relationship 6, which is again an additive relationship. Now what we are going to do is, actually we can directly calculate that value with a formula, or we can find that value through the compound interest table directly. However, what we are going to do is we are going to search for A over F value under 8% interest rate for 5 years. And that is just going to be 1.8666. And the multiplicative inverse of the sinking fund factor is going to be 0.17046. And if you sum that value up, I'm sorry, the multiplicative inverse of the compound amount factor, we are interested in the sinking fund factor. The sinking fund factor is equal to 0.17046. And if you add the interest rate as decimal to that, you will get 0.25046. And that is A over P value under 8% interest rate for 5 years. Now let's check these values, 0.17 here and 0.25 here approximately. Now let's check, I'm sorry, 5.86 and 0.25 here. So let's check these values from the table if this is true. Now if you go back to 8% table for the fifth row, you get 5.8666 and 0.25046 here. So this relationship is actually true. Okay, so let's go back to our presentation file again, and we are going to go through our last relationship, which is the limiting relationship. And it says the capital recovery factor, I'm sorry, yes, exactly, capital recovery factor. For uniform series capital recovery factor under I% interest rate for n years goes to the decimal interest rate as n goes to infinity. Namely, the capital recovery factor for a infinitely long period of investment is just the interest rate as decimal. I mean, if you are taking a loan of $100 from me, and if you say that to pay this in 10 years, and if I am going to apply you, for example, 5% interest, and we can calculate each of your installments that you need to pay in the end of each year, right? So we can use the capital recovery factor, and we multiply it with the initial principal that you have borrowed, which is $100, and we can calculate your installment size. Now, if you say, I would like to give that money in 100 years, not in 10 years, but in the end of each year, for 100 years, I'm going to repay you an installment. Now, we need to calculate that value again by multiplying the initial principal with a capital recovery factor, but this time it is supposed to be calculated for 100 investment years. Now, 100 is a sufficiently large value, and for that sufficiently large value, you will realize that it is going to converge to the decimal interest rate directly. So if you take, or if you borrow $100 from me, and if you say you would like to pay this in 100 years, as equally spaced installments at the end of each year, and if I am applying a 5% interest rate, then you are going to pay me $5 in the end of each year. You are just going to pay the interest for each year, okay? So this means what? The equivalent uniform series for a very long period of investment, okay, for the initial principal is just the interest itself. So you are renting my $100 for a very, very long time. This means you are just going to pay the rental fee, which is $5 under 5% interest rate. Okay, so how this is true can be shown because we know the capital formula, and as n goes to infinity, we need to take the limit of this capital recovery factor. Remember, the A over P value, capital recovery factor, can be decomposed as the decimal interest plus the inverse of the compound amount factor, which is the sinking fund factor. Now, if you take the separate limits of the first component and the second component, the first component will remain as I, and in the second component, we have 1 plus I to the power n, which goes to infinity as n goes to infinity. Therefore, the second component is just going to converge to 0. And here we have the remaining value I. Now, please check the compound interest table. Once again, as you can see, for 8% interest rate, or in other words, 0.08 interest rate as decimal, the capital recovery factor converges to 0.08 as n goes to infinity. Check any other page. Check any other page. For 9%, interest, the uniform series capital recovery factor column will converge to 0.09. For 10%, it will converge to 0. Okay, it is just the case. Why is the reason for that? Because of the previous relationship. Remember, 1 over the second column value plus the decimal interest rate will become the third column. But 1 over the second column value is converging to 0 in any way because the second column, the compound amount factor, is increased very fast to infinity as the number of investment years goes large. Therefore, this value converges to the decimal interest. Okay, so for a long period of time, the uniform series capital recovery factor is just going to be equal to the decimal interest. Now let's go back to our presentation file and solve our final question and complete this week's lecture. All right, so it says if a person wants to take $10,000 in the end of each year for 70 years, and the yearly compounding interest rate is 8.5%, how much money should she invest today into the savings account? So for 70 years, this $10,000 that the person is looking for is the uniform series single installment, and we are just going to calculate the present value right now. How much principal should we invest in that savings account so we can get this $10,000 for 70 years? Now, how can we calculate that value? We can multiply the installment size $9,000 with a uniform series present worth factor for 8.5% interest for 70 years. And that value, P over A, is equal to the reciprocal of A over P under 8.5% interest rate for 70 years. So we are going to take the power to the -1 for that value to calculate uniform series present worth factor. According to the relationship that we have just explained, limiting relationship, for a sufficiently large number of years, which is 70 here, and can it be assumed as a sufficiently large? Now we'll see. We will see if it can be assumed or not. Now we are just going to take that value as 0.085, which is the decimal interest rate. So we will assume that the limiting relationship may apply here. And then the necessary principal amount would be $117,647.1. Now the true answer can be computed applying uniform series present worth factor formula directly. And if you apply this formula directly, you would get the true answer as $117,257, which is almost $400 short than the approximate answer. So as you can see, 70 is a very large number, sufficiently large number to make a moderate approximation here. So the approximation is not very good, but not very bad either. So we can assume that 70 is a sufficiently large number of investment years, and we can directly take the uniform series capital recovery factor as the decimal interest rate for that example. However, as I have always, I have previously said, and I always will say, if you really want to get the correct value, exact value, you need to do what? You need to calculate it through the formula. Okay, this is the end of the third week's videos, and please perform your reading assignments and make the readings regarding to these relationships and the gradient series analysis from your textbooks. Okay, have a nice week.